Okay. All right, so today, this is 7-2. I want to discuss with you how we're going to apply multiplying radical expressions and how you will divide some radical expressions. And the property that you'll use in all these lessons is if you are multiplying the common root, so whatever to the nth root, you get to multiply the radicands. That's the fun word in math. Say radicand. So the number on the inside, that's the radicand. That can be multiplied if it is a common root. Example, put this right there in your booklet. If you're taking the square root of, let's just say, the square root of 8 times the square root of 2. To make this easier, because they're both square roots, you can make it square root of 16. You can go ahead and multiply the radicands, which simplifies to 4, right? That's how that property can be applied. It's applied in a lot more ways. You can use it with letters and dividing radicals. If you're dividing a common root, square root of letter A, the nth root of letter A over the nth root of letter B, if they're both the same root, you can divide the radicands. And that could be helpful. An example of that. Here, put an example of that right there. If you were taking the square root of 24 over the square root of 6. The square root of 24 doesn't have a square root. 6 doesn't have a square root. Can I divide and make that easier? Since they're both square roots, that could be the square root of what? What's 24 divided by 6? So I can rewrite that as, I can combine that through division and just write it as the square root of 4, since they're both square roots. And, of course, that makes 2. See those two properties? Good with that so far? Now, there's one more thing I want you to see on this page. There's a process called rationalize the denominator. Say that. Rationalize the denominator. That means it's a process of getting radicals out of denominators. It shows you right here. Example. 1 over square root of 2. You never would want to leave a square root or radical sign in a denominator. That's kind of like a simplification rule. Where do we never leave a radical sign? And we don't ever leave one in a denominator. And if we can divide, like right here, there was a radical sign in the denominator, wasn't there? See that one? Was that a radical sign in the denominator? Yes. If I can divide, and now no longer do I have a denominator. But if I can't divide, right here, 1 over the square root of 2, I can't divide. I have to rationalize the denominator. Would you like to know how to rationalize your denominator? Yeah. So I would love to know how to rationalize your denominator, you say. So it's a process like this. So let's say you have the square root of 9x over the square root of 2. Write this with me on your paper somewhere. Don't stare at me. Write it somewhere. Now, they're both square roots. You always ask yourself, can I divide 9x divided by 2? Does that divide easily? It's not really going to help me any. So the part of rationalizing the denominator, the RTD, I can take the denominator times something so that it's no longer a radical. I don't know what the square root of 2 is, but if I took the square root of 2 times the square root of 2, what do you think it equals? Square root of, which is 2. So when you take this here, square root of 2 times square root of 2, it ends up at square root of 4, which is 2. So it magically, the radical sign is no longer there, is it? Hey, do you know the square root of 2? You know that 2 has a square root, right? There is something. If I multiply something times itself, I could get 2. It's an irrational number. I don't have to worry about what it is. Whatever that square root of 2 is, if I take that square root of 2 times square root of 2, what should you have? You should have 2. If I took the square root of 75 times the square root of 75, I should have 75. You got that? Like whatever its square root is. So right here, by taking this denominator times itself, the radical sign goes away and it becomes 2. On top, now here's the deal with similar fractions. You ever dealt with similar fractions? If you do something in the denominator, what do you got to do in the numerator? The same thing. So whenever I multiply the denominator by, I multiply the numerator by. So then I end up with, that's right, square root of 18x. And is there anything in the 18 that can be brought out? Yes. What can come out of the 18? 9. We can think of 18 as 9 times 2. So what does it come out as? What will be on the outside of the radical sign? 3. Thank you. 3 is the square root of 9. What stays in? And the x. Neither one of those had a square root, and the 2 would also be out there. Or, excuse me, the 2 would still be in the denominator. That's what I meant to say. So this is a process of rationalizing the denominator right here in order to get a radical sign no longer there. This would be the simplified version of that. This is easy when it's square root times square root. You just take it times itself. What if it was like this? 4th root of 2x over 4th root of 3x squared. Here and here. There is not a 4th root of 3, and x squared doesn't have a 4th root either. So I could try to divide, but then I would still have a 2 over 3 and x. So I can't divide here to help me. That's a good question. So let's play this out. If we multiply, I'm going to show you, here's the wrong thing. If I just follow that pattern, take it times itself, follow along, students. You are smart. This is deep level thing. If I take it just times itself, 4th root of 3x squared times the 4th root of 3x squared, I end up with, that would be the 4th root of 9x to the 4th. Does x to the 4th have a 4th root? Yes, it does. Can somebody tell me the 4th root of x to the 4th? X. So it could be written as an x. But does 9 have a 4th root? No. So I can't just take this time exactly by itself. I got to think, I need to multiply it times something that gives me a radicand that has a 4th root. So on the x's, I just had to have 2 more. Make it x to the 4th. On the 3, if I just take it times another 3, I got 9 there. So I have 1 3. I put another 3 in there. So right now, how many 3's do I have? So I could take the square root, but how many 3's do I need? 4. So instead of multiplying it by 3, let's do it the right way now. So if I took that denominator, 4th root of 3x squared, I would multiply it times the 4th root. Now we already said the x squared is okay, so we'll leave it there. But I don't want just 1 3. I need, how many more 3's? How many more 3's? 3. I already have 1. So what is 3 3's? 3 3's. 3 times 3 times 3. What is it? 27. That's the 3 repeated 3 times. And that would give me the 4th root of 81. Again, I still have x to the 4th. which would simplify to, like we said, 3x, wouldn't it? The fourth root of 81 is 3. The fourth root of x to the fourth is x. So this rationalizing the denominator, when it's square roots, yeah, you just say take it times itself. But when it's fourth roots or third roots, you got to think, I got to get enough repeated factors in there that it would have a fourth root or third root or whatever it might be. Deeper thinking. And if I did it to the numerator or the denominator, I would do it to the numerator as well. Let's see, we'd put it right here. Fourth root of 27x squared. So 27 times 2, yep. That would give me right over here in this numerator. Actually, right here, we'll do it the right way. We'll put it right here where it's right. Fourth root, that would be the fourth root. What's 27 times 2? 54? Yes, yes, yes. And x to the third, x times x squared. Does x to the third have a fourth root? No, there's not enough of them. I would need at least 4 of them there to have a fourth root. That x right there would stay in the radical sign because there's not a fourth root. It has to stay in there too because I don't know. I know like 54 is, if you think of 54 as 27 times 2. So 27 is 3, 3, and 3. 2 is 2. So I can't rearrange anything there to get something 4 times. No, no. If there was a number there that had a fourth root, we'd bring it out. All right. So rationalizing the denominator can be really simple when it's square roots, or a little more complicated whenever it is different roots. You following that, guys? Okay. So let's look at your worksheet. You've been given this worksheet. Multiples of 3 plus 34. All right. We're going to apply the properties. It says multiply and simplify. Apply the properties we just learned. There is a cube root and a cube root. And I got a lot of stuff on the inside. Cube root. I have a 50 and a 15. What do you see a lot of with 50 and 15s? What factor do you see repeated a lot? No, with the 50 and the 15, there's a lot of 5s in there. How many 5s are in 50? No. Oh, I see what I mean by factor-wise. Like 50. Isn't 50 25 times 2? How many 5s are in 25? 2. Think of it as a factor. 5 times 5 times 2. Now think about 15 over here. How many? I see what you're saying. I know that's kind of confusing. I'm not thinking of it like adding them up. I'm thinking about multiplication factors. Repeated bases. So in my brain, I see 50 as 25 and 2. I see 15 as 5 and 3. This will help me simplify if I think of it this way. So over here, I'm going to write this as the cube root of 6 times 2 and 3 make 6. What's 25 times 5? 125. I'm going to, now, obviously, I could have multiplied the 50 and the 15, and I would have 750, right? I could have done that. I could have had 750 in there. That's fine. But I didn't need 750 in there because I'm wanting to try to figure out if anything has a cube root. And the 5 repeated 3 times, 5 times 5 times 5, so that shows me there will be something with a cube root. You follow my thought process there? That's tricky, but we can do it. All right, now on the x's, how many x's will be in there? 2. How many y's? 3. How many z's? 6. So that is just the process of multiplying the radicands. Now I can actually take the cube root. What will come out? What will 125 come out as? 5. leave the 6 in. Does the x squared able to come out? Does it have a cube root? No, we'll leave it in. Does y to the third have a cube root? It has. Yeah, you're not asking why, you're saying why, aren't you? Yeah, y times y times y is y to the third, isn't it? All right, what about z to the 6th? Does it have a cube root? Z squared, very good. And that would be my answer. I know that's kind of hard to see maybe for you, but it's 5yz squared, cube roots of 6x squared. The 6 stayed in and the x squared stayed in. Because the 6 does not have a cube root. A root is a repeated base. So yes, 6 is 2 times 3. I'm talking about this 6, not that 6. Great question. That 6, yeah, that 6 is an exponent, isn't it? And an exponent shows a repeated base. So z to the 6 is z times z times z times, repeats out. So let me rewrite this for you real fast right here. Z to the 6, talking about a cube root. Why does it have a cube root? You can divide when it comes to exponents. It's because z squared times z squared times z squared, there's its cube root. Something multiplied times itself 3 times. 1, 2, 3. So z to the 6 does have something that can be multiplied times itself, a repeated factor 3 times. Are you okay with that? Cube root of 6, there has to be something in 6 that is repeated factors, right? Well, 6 is only 2 times 3, right? There's no factor in 6 that's repeated. Follow that? Now, we did take out the 150. No, 125. I meant to write 125. Scratch that. We did simplify the 125, didn't we? It's because 125 is a repeated factor of 5 times 5 times 5. So if it has a factor that can repeat, that has a cube root. That simplifies to 5. And that is why the 5 is out and the 6 stayed in. Does that help? Good, guys? Y'all keep talking to me. I want to see good looks. All right, number 6. That's a good challenging question to start the paper with. They're not all that challenging. That's okay. Number 6. We'll do it right here. If there is something in front, like the 9 and the 3, we multiply them. So what do y'all think I could rewrite this as? Almost 27 square roots of 2y. The property says if you're taking square root and they're all factors, this is all multiplied, I can multiply the radicand. So I can combine them into just the square root of 2y. That's all I can do, guys. 2 doesn't have a square root, and y doesn't have a square root. So square root of 1 is 1, sure. No, y is not a repeated factor. It's just y. It's not y times y. It's just y. Good question. All right, now let's go to number 9. That was a simpler one. Not a lot there. 9, x squared over 3y. Can I divide? Is it dividable? No. Since it's not dividable, I need to rationalize. All right, we're going to rationalize it. I'm going to put it right here on this paper. Then we have plenty of room. 3 roots. It's x squared over 3y. Like that. See it? I'm going to rewrite it as 3 roots of x squared over 3 roots of 3y. Rewrite yours that way. Play along. It's the only way this will make sense. It can be written either way. These can be in 1 or they can be in 2. That's what the property helps us know. 3y does not have a cube root. The only way to get it out there is rationalize the denominator. So if I take it times the cube root of something, I don't need that many 3's. If I do 27, that's 3 more 3's. If I do 9, very good, that's 1 3 there and 2 more 3's there. What about on the y side? How many y's do I need in there? 2 more. I have 1 there and 2 there. So 9y squared. Let's do that on the top. Cube root of 9y squared. So that is the rationalizing the denominator, multiplying the denominator times something that allows the radical sign to disappear. What would that denominator now equal? Cube root of 27y cubed. Yes, which is what? What is the cube root of 27? What's the cube root of y to the third? So 3y is our, by rationalizing, we were able to get the radical sign off and it leaves the 3y. The numerator is still cube root of something. Yeah, we did. There, let's multiply here. What's the number? Nothing has a cube root. They have square roots, but we don't have cube roots, do we? Guys, this is deeper thinking. This isn't like, hey, I'm giving you a spoonful of something easy, making you think today. That's good. Really, really good. We need to flex our brains today. All right, we rationalize the denominator. Good job. Now we're on number 12. 12 is the cube root of 3a over the cube root of. Let's get through this one, maybe one more. Hey, this is awesome. I really can't divide. I can't do 3a divided by 4b squared c, and it helped me. So what am I going to do? Say it. Rationalize, do it. Everybody write RTD on your paper. Rationalize the denominator. Some of you, I don't see you write anything. I ask you to write, but you don't write anything. I don't get that. You're just like saying, I don't believe what you're saying, Mr. Bush. You're not telling me anything that's valuable to me, so I'm not going to do it. That's kind of disrespectful in Mr. Bush's eyes. I'd rather you do what I ask you to do. All right, so we got to find a cube root thing. What am I looking at with 4 there? What do you see when you look at 4? No. Think a little bit deeper. What do you look, when you see 4, what do you see? 2 times 2, so you already have 2 2's, don't you? Let's just do one more 2. I like that. On the b squared, what do we need? One more b. On the c, what do we need? 2 more c's. You're on the right track. So we didn't have to go all the way up to 3 4's. We stopped with 3 2's. We do it there. Let's do it here. 2bc squared. We'll do it on top and bottom. The bottom. You multiply that out, what's the number going to be? So it's going to be cube root of 8, which is what? 2. Cube root of 8 is 2. We're going to have b to the third. What's its cube root? We're going to have c to the third. What's its cube root? So the denominator, the radical sign goes away. The numerator will be the cube root of 6. Y'all agree? A and what? B. C squared. Does 6 have a cube root? Does A, B, C squared? No. So we can't go any farther than that. Mind-blowing stuff, but we're applying this property somehow. All right, we got time for So we just did really challenging. We did some of the hardest ones already. Go to number 15. It just says multiply and simplify. Square root of 3, square root of 27. Hey, I like what you said. It's 81, isn't it? Yeah, that one's a lot simpler. 3 times 7 is 81. It has a square root. It is 9. What does 81 also have a lot of? What does 81 got a lot of? 3s. We could take a fourth root of that if we wanted to. Because it's 3 times 3 times 3. It's a lot of 3s. Okay. Let's go to 18. Maybe we can end right here. 18, we got some cube roots. If we multiply, we would have the cube root of what? Tell me what would be inside there. All right, nice and easy. Everything has a cube root. What's the cube root of 8? X to the third. Y to the 9th. Y to the third, right? Now, I will tell you, there are times that when you multiply and you could end up with something all right, so we were there earlier. What if you did this? What if you took the square root of x to the 7th? Just land on this thought. What's the square root of x to the 7th? No. But can we get some of it out of there? What can we take x to the 7th and break it down to? 4th and 3rd, or 6 and 1. And you want to break it down. You want to peel off the 7, this 1, and you want to leave something that has the largest amount that you can take a square root of. So that could be rewritten as x to the, what's the square root of x to the 6th? 3 square roots of, what stays in the radical? X. So sometimes you have a exponent, a repeated factor, that you can't divide that, so you have to break it down inside there to where you can pull some out. Okay, so today we got through, what did we get through? 18. If you want to go ahead, please, after what I just showed you, work on 21, 24, 27, 30, 33, 34. There's a few more there. You can look at them, and we will finish giving the answers and explain this tomorrow.